Welcome again. As you have understood during this course, we focus on a case for making propanediol using microorganisms. Let us now have a look how this production will look like. Propanediol is a molecule which has the composition of C3H8O2. You would like to use microorganisms to make PDO from sustainable substrate, for example glucose. For understanding the production process of any biotech product, it is useful to write down a theoretical product reaction, which is a reaction for making 1 mole product. And when writing down this product reaction, you want to find the best possible stoichiometry where the lowest amount of substrate is consumed. Therefore, this reaction is written in the absence of oxygen, because oxygen consumption relates to substrate oxidation and it is therefore unwanted in the theoretical product reaction, because it increases the amount of substrate consumed to create 1 mole PDO. However, other compounds like proton, water, carbon dioxide are always involved in the theoretical product reaction. We can calculate this reaction by using propanediol as an example. The theoretical product reaction starts with 1 mole propanediol on the right side. Then you have to make a choice for a feedstock, which will supply the carbon atoms for the product. In this case, we assume this is glucose. From this, we can complete the reaction by adding carbon dioxide, water, and protons. The stoichiometric coefficients A, B, C, and D are unknown values for our theoretical product reaction at this point. Note that in this reaction, all the consumed compounds, such as glucose, have a negative sign, and in this case only glucose, and therefore A will be negative. And the produced compounds do have a positive sign, and therefore B, C, and D are positive. But we know that all the elements and charge going into the reaction need to come out. Therefore, finding A, B, C, and D requires to write down the element and charge conservation relations. Let us take carbon conservation as an example. The glucose carbon equals 6A. The PDO carbon equals 3 multiplied by 1 because of the 1 mole propanediol and the 3 carbons in the PDO. And the carbon dioxide carbon equals 1B. And all of this should add up to 0 because of the carbon conservation. We can do so for the other elements, H, O, and charge, and we have now 4 linear equations with 4 unknowns, which means we can solve this to find the values for A, B, C, and D. This calculation leads to the theoretical product reaction for PDO. From this reaction we learn 2 important things. First of all, we know now the absolute minimum glucose requirement, which is 2/3 mole glucose per mole PDO. This is an important value to judge your variable costs of your fermentation process. Secondly, you can see whether the product could supply energy for the organism. From glucose to PDO, this PDO reaction shows that this is indeed the case because the Gibbs energy of the reaction calculation tells you that 1 mole PDO produces 110 kilojoules of Gibbs energy. And this thermodynamic calculation shows that the energy is there, but we cannot decide whether organisms can convert this energy into biological useful energy such as ATP. Following this energy consideration, it is now important to distinguish 2 product classes: energy producing and energy consuming products. The first class of products generates energy in the form of biological energy. If this is the case, then you have an anaerobic process, which means that no oxygen is needed for the organism to grow and to produce. The theoretical product reaction of PDO, which we just derived, shows that in principle it is an energy producing product reaction. Thus, it would be possible to perform this production of PDO anaerobically in the absence of oxygen. Unfortunately, research has not succeeded in this yet. The second product class consumes energy. Therefore, the microorganism needs a source of biological energy which comes most efficiently from the oxidation of substrate with molecular oxygen. And for this product class, the fermentation therefore needs to be aerobically, and we need to supply oxygen as nutrient. Most microbial production processes at this moment are aerobic. Besides the theoretical product reaction, there is an other reaction which is central in the design of our PDO process. And this is called the process reaction. In this process reaction, you quantify the uptake and secretion rates of all important nutrients, but also all the products and byproducts that are being made. As shown in the figure, this involves many Q rates, not only for growth, substrate and product, PDO, but also oxygen, carbon dioxide, ammonium, water, protons and even heat, indicated by the symbol Q. By combining all these Q rates together in one reaction, you can get the process reaction, which is the basis for process design. It is now very convenient to normalize this process reaction to the production of 1 mole PDO. This is done by dividing all the coefficients by Qp. This process reaction has important properties. Its stoichiometric coefficients are Qi over Qp ratios, which can be positive in mole I produced per mole PDO produced, or negative in mole I consumed per mole PDO produced. The coefficients represent the process stoichiometry, which depends on the Q rates, and which are therefore not constant. So they are not constant. In absence of growth or oxygen consumption, the process reaction reduces to the theoretical product reaction, which we just discussed. The process reaction is complicated, but it is the basis of process design and deserves our attention. I showed you that you can calculate the theoretical product reaction from only knowing the product and substrate composition. The remaining obvious question is how to obtain the process reaction. Here we need the values of the Q rates, for which we will need the black box kinetic model to be discussed in the next unit. So therefore join us next unit for more technology for bio-based products.